Hi guys, Justin here, chemistrynotes.com, and we are on video number 2 of section 13. Section 13 is chemical equilibrium. So in video number 1, the last video, I introduced to you what equilibrium was between reactants and products and the dynamic steady state that exists. And I didn't give you the equilibrium expression. I didn't talk about the equilibrium constant. I wanted to talk about that in today's video. So today is when we're going to get to some of the math that's involved with chemical equilibrium. Okay? So at the top of page 1 of our notes, it says a general expression for chemical equilibrium. Well, here I have a reaction, very generalized. J moles of A plus K moles of B yields L moles of C plus M moles of D. The equilibrium expression is K equal, that's a capital K, equals the concentration of products over the concentration of reactants. You'll notice that the concentration of products, each product is raised to the power of its coefficient, okay? So K is my equilibrium constant, and it's unitless. Okay, I'm not going to get into an argument about how K is not unitless. We're going to assume it's unitless. And then the brackets, as you know, are concentrations. Now those concentrations are concentrations at equilibrium because K is what? Equilibrium constant. Sometimes you see a little sub EQ written to the right of the brackets. Now, if the reaction is written in reverse, then we would have K prime equals A, concentration of A to the power of J, concentration of B to the power of K, and the whole thing is just flip-flopped, so K prime is 1 over K. All right? Very similarly, if I were to multiply my forward reaction through by a coefficient, say 4, then we would get the following equilibrium expression. So I have 4J A plus 4K B yields 4LC plus 4MD. Well, my equilibrium expression, it would be K double prime equals concentration of products over concentration of reactants. And this is a forward reaction, so I write it as such. Except now the coefficients are 4J, 4K, 4L, and 4M, so my powers are different. So in this example, K double prime is just my initial equilibrium constant, K, to the 4th power. All right, so that's some of the manipulations you can do. You want to focus on the very first one I had for you, which is capital K, the first one. That's the one that we're always going to use. And let's do an example to show it. Consider the following reaction and the following equilibrium concentrations. N2 gas plus 3 moles of H2 gas, and it just so happens it's at 127 degrees, and that yields 2 moles of NH3 gas. And then they're nice enough to give us the equilibrium concentrations here, H2 0.0031, N2 0.85, NH3 0.031 molar. These are concentrations, right? So big M, molar. Okay, what are we told to do? Because so far they've just given us information. Well, we have our first question in A. A says, hey, calculate the equilibrium constant K. Well, we have just learned that K is equal to products divided by reactants, and then we use the mole ratios and the coefficients to, if we need to, raise things to the power. So K is the concentration of NH3 squared, all divided by the concentration of N2, all divided by the concentration of H2 to the 3rd power. If you do this, you should end up with 3.8 times 10 to the 4th. All right, and remember, there's no units for K. The equilibrium constant has no units for us anyway. All right. B, second question. Hey, calculate K for the reverse reaction. Well, the reverse reaction, our products are now our reactants. So we're moving right to left. So I just flip-flop this. So if I had recognized that K prime is 1 over K, I could simply do 1 divided by what I had solved for on the previous page. 1 divided by 3.8 times 10 to the 4th is equal to 2.6 times 10 to the minus 5th. All right, C. This is our last question for this example. Calculate the equilibrium constant for the following reaction. And it's just the exact same reaction, but it's been multiplied through by 1/2. So if it's multiplied through by 1/2, then I'm going to raise my K to the power of 1/2. But we'll draw this out and we'll write it all out. We've got K double prime equals concentration of NH3 divided by the concentration of N2 to the 1/2 divided by H2 concentration to the 3/2 power. It's just K to the 1/2. That's the same thing as the square root of my equilibrium constant K. So I take the square root of 3.8 times 10 to the 4th, and I get a value of 190. Just remember, you don't multiply K through by 1/2 the way the equation was multiplied through. You raise it to the power of whatever you multiplied that equation through by. All right. Double lines, moving on just a little bit here. It says there's only one equilibrium constant for a specific reaction at a specific temperature or at a particular temperature. Equilibrium constant K is temperature dependent, right? You can imagine if you increase the temperature, you're going to affect where equilibrium lies in an equation, right? Does it lie more towards products, more towards reactants? Is this an exothermic reaction or an endothermic reaction? I just want you to know that there's one value for K at one specific temperature, all right? And then it says, okay, well, there's one value for the equilibrium constant at a specific temperature, but then there's an infinite number of equilibrium positions. So what is an equilibrium position? Well, an equilibrium position is just a set of equilibrium concentrations. In the last example, and it looks like I'm actually writing down the same example, but I gave you at the last example problem, right? The given, I gave you 3 equilibrium concentrations for H2, for N2, and for NH3. That was a equilibrium position. That was a set of all 3 equilibrium concentrations for reactants and products. Okay, and let's talk more now about equilibrium positions as I introduce something called, well, I don't want to get there yet, but let's just do this sample problem. We have N2 gas plus 3 moles of H2 gas yields 2 moles of NH3 gas. So initial concentration for an experiment 1, I'm listing the initial concentrations of all my reactants and products. I'm doing that right now for experiment 1. I'm now writing equilibrium concentrations for my fictitious experiment 1, N2, H2, and NH3. You notice that the initial concentrations have that little sub-zero knot. We're used to seeing that, right? And then if I do my equilibrium concentrations and put them into my equilibrium expression and solve for K, 6.02 times 10 to the minus 2. All right, now I have fictitious experiment number 2. We're running a mock experiment here on paper. So this one has different initial concentrations, and then once you let that reaction happen, you get to the second column, which is the equilibrium concentrations. And if you put the equilibrium concentrations into the value for K equals NH3 squared over N2 over H2 cubed, you get the same equilibrium constant because this reaction is being run at the same temperature. So what do you think as I put down initial concentrations for experiment 3 and now as I write down my equilibrium concentrations for experiment 3, what do you think my value of K is going to be? Yes, it's going to be 6.02 times 10 to the minus second. Now, the equilibrium concentrations, that's the column I'm using to solve for K. We don't use initial concentrations for that. All right, so let's take a look at this dashed line circle, right? That is an example of an equilibrium position. I know the concentrations at equilibrium of all my reactants and products. All right, so to elaborate on that little dotted line circle, it says all 3 sets of equilibrium concentrations. What does that mean? All 3 sets of equilibrium concentrations. It means the H2, the N2, and the NH3. Those are my 3 sets. And I had that 3 times. So all 3 sets of equilibrium concentrations, in other words, an equilibrium position, gives rise to one equilibrium constant, K. All right, now, again, that's under the assumption that we're doing all 3 of those experiments on the last page of notes at the same temperature. All right, double lines, moving on. It says equilibria involving gases can also be described in terms of pressures. Now, I haven't really made too much mention of it. I am going to later on, but up until now, every component, reactant and product has been a gas. Okay, so equilibria involving gases can also be described in terms of pressures instead of concentrations, right? If we use PV equals nRT, P equals nRT over V. Well, what's N over V? N is units of moles, V is liters, mole per liters. That's a molar, that's concentration C, right? So P, our pressure, is just equal to our concentration C times RT, all right? Now, I could have written P equals C times RT to the delta N, all right? But I'm just going to leave it as P equals concentration times RT, all right? So for the previous reaction, my equilibrium expression was K equals concentration of NH3 squared divided by concentration of N2 divided by the concentration of H2 to the third. My Kp, or my equilibrium constant in terms of pressures, is the partial pressure of NH3 squared divided by the partial pressure of N2 divided by the partial pressure of H2 cubed. So it says that in the box, that's the partial pressure of each gas at equilibrium, all right? So let's do an example. It says, calculate the value of Kp. So now I know I'm calculating the equilibrium constant in terms of pressures instead of concentrations. Calculate the value of Kp for the following reaction at 25 degrees Celsius given these equilibrium partial pressures. So this is just going to be a plug and chug, right? I'm going to have, I got the partial pressure of NaCl at equilibrium. I've got the partial pressure of NO at equilibrium, and they're also giving me the partial pressure of Cl2 at equilibrium. And then, of course, the next is the balanced equation, right? So Kp is partial pressure of products divided by the partial pressure of reactants. And then we can't forget the exponents where necessary, all right? So in this particular case, Kp is equal to the partial pressure of NaCl squared divided by the partial pressure of NO squared divided by the partial pressure of Cl2. If you do the math and plug in the numbers that you're given, you get a Kp value of 1.9 times 10 to the third. And again, Kp has no units, just like Kc. All right. All the Ks that we've been using up till now are in terms of concentration. If you see a Kp, that means it's in terms of partial pressures. All right. So a lot of notes or a lot of lectures or a lot of textbooks, instead of just having a plain old capital K, they'll have a capital K with a little c. All right. But I just use plain old K. All right. So that's it for section 13, video number 2. If you like the way I do these handwritten chemistry notes, I have the full course general chemistry notes and full course organic chemistry notes. If you go into your second year of chemistry and take organic, you can get them all at chemistrynotes.com, and I'll see you back here for video number 3.